Okay. So we're first just gonna kind of remind you about special right triangles. Again, you probably did a lot of work with this in geometry where using these special right triangles, essentially if you know one side length, you can find the others because they all follow a similar ratio. Okay, with as long as these angles, so if we have a triangle with angles 30, 60, 90, 45, 45, 90, again, all those side lengths have a similar ratio. So these are also the building blocks for what we will get to probably next week in building what's called the unit circle. So knowing these triangles, that's kind of the foundation for it. You don't need to have these memorized. It's more just going to be you kind of working with these special right triangles. You probably did the bulk of this work back in geometry. So a 30, 60, 90, that's kind of the name of the triangle. That's referencing the degrees of each angle. So a 30-degree angle, 60 and 90. Let's label this based on, if you want to draw to scale, it looks like this is the shorter side. So this should be the 30 degrees. And this is the longer side. So that's your 60 degree. And then again, knowing if we know one side length, we can go ahead and use these ratios. So we have a root 3, and negative, or excuse me, and then 2a. A is the shortest side. And then the next shortest side is a root 3. And then the longest side is 2a, or the hypotenuse. Okay, so it just follows those ratios. And again, I'm just going to kind of introduce these. We'll see them here in a second with values actually kind of played out. And I'll also talk about what this A is here in a moment as well. All right, then the 45, 45, 90, based on how this triangle is drawn, that 90 degree is actually that top angle there. And then leaving the other two angles to be your 45 degrees. And this one's a little more obvious, right? With two side lengths being just A, those are going to be the legs. This is kind of a lot like that isosceles triangle problem we had yesterday, making the hypotenuse here a root 2. So essentially what we're going to use these for is to find specific values of these angle measurements, so of 30, 60, and 45. And again, that's kind of the foundation for what you'll see next week with the unit circle. This isn't any different than us doing SOHCAHTOA, and that's all we're going to do with these. But I do just want to kind of show us a couple things with where these values come from and how they show up in actual triangles with side lengths. Okay, so starting with this 30, 60, 90, knowing that, so everything's filled in, that's why we don't need to worry about this all that much. Let me just kind of show you how we could use this. Let's pretend we didn't know 1 and root 3 and we were only given 2, but we did know that it's a 30, 60, 90 triangle. Well, this is 2, and that's the hypotenuse. Remember that in kind of like the general triangle, the hypotenuse is equal to 2a. So I could say 2a, so the ratio is equal to 2 because that's the actual hypotenuse length here, allowing us to find the value of a. When I divide both sides by 2, we get a to be 1. And so then if I follow how that kind of general triangle was labeled, our shortest side was just a, or the side across from 30 degrees. That's why here the side across from 30 is just 1, our value of a. And then the longer side is a times root 3, a being 1, so 1 times root 3 is root 3. Okay, so that's what you would have done in geometry with these 30, 60, 90. Again, you're not going to have to do that a whole lot here, but I want to just show you why we kind of started with that before we actually find these values. We can do the same thing with the 45, 45, 90. Think about what a is. In this case, a is 1. So our two legs are the same, are 1, and then that hypotenuse is a times root 2. Well, it ends up just being root 2 here, okay? These are the actual triangles. Actually, no, they're not. But these 30, 60, 90, and 45, 40, 90, like I said, will be used for what we do with the unit circle. So now what we're going to do is we're going to find the values of sine of 60, cosine of 30, et cetera, just by doing SOHCAHTOA. Okay, so maybe I'll just do a couple, and then this is a good warm-up for us. So if I have sine of 60, I know that sine is the opposite side over the hypotenuse side, so it's root 3. over 2. You know what? Why don't we just have you find the rest from there? Okay, think about which reciprocal functions correspond to what when they're in radians. Think about what radian amount that corresponds to in degrees. Okay, well, let's this be our warm-up. Give you about 3 to 4 minutes to work through these, and then we'll go over those. All right, so let's start with the values of A through D. Again, I'm just thinking about SOHCAHTOA. Okay, so with sine, I did that one for us, opposite over hypotenuse. Cosine of 30 is the adjacent side over the hypotenuse side, but I have to use that 30-degree angle. Now, when I do the adjacent side over the hypotenuse, I get the same thing as the value of sine of 60. Okay, so sine of 60 and cosine of 30 are actually equivalent, and we're going to talk about, there's a name for that. It's called a cofunction. We're going to do that tomorrow. Okay, we'll kind of bring those identities in. But that's real common, okay, where sine of some values are equal to cosine of values as well. We can get the same things there. All right, sine of 45, now I've got to use that 45-degree triangle. Again, doing the opposite over the hypotenuse. But denominators need to be rationalized, and that's a big piece of all this trig stuff, is getting rid of those square roots out of the denominator. So I multiply by root 2 over root 2, giving me root 2 over just regular 2, okay, for the simplified value there. Then tangent of pi over 4. We should know whether you need to convert it or not, but pi over 4 ends up being equal to 45 degrees. So I'm actually still using this 45, 90. The opposite over adjacent is 1 over 1, which is just 1. Questions there on A through D? Okay, so now over to the reciprocal functions. What made this a little bit straightforward is, like, E is the reciprocal of A, right? So sine of 60, cosecant is the reciprocal of that. So one way to kind of think about the reciprocal functions is think about what reciprocal means. It means to flip the values. So I start with, what do I know about sine? I know that sine is the opposite side over the hypotenuse. So if I flip that, cosecant is the hypotenuse side over the opposite side. Getting this to be 2 root 3. I can multiply by root 3 over root 3 to rationalize the denominator. Okay, so it ends up being 2 root 3 over 3. Now, one thing that we can also do is, if I know that cosecant of 60 is a reciprocal of sine of 60, I can take this value of sine of 60 and just simply flip it. I can take the reciprocal of that, right? And that's where I get this 2 root 3 from. So there's lots of ways of how we can find these values of the reciprocal functions, whether that be just taking our original value of sine of 60 or thinking about the reciprocal ratio within terms of the lengths of the triangle. Everyone follow me there? Okay. So secant, reciprocal of cosine, so it's the hypotenuse over the adjacent side. Once again, we need to rationalize. Ends up being the exact same value as cosecant of 60. Cosecant of 45, reciprocal of sine of 45. What's nice about that one, and this is where, like, if I were to flip the value of sine of 45, root 2 over 2, there's a lot more simplifying that needs to be done because the square root ends up in the denominator. So a lot of times that's where I'm like, okay, what's going to be the easiest way to get there? And in this case, it's actually thinking about the hypotenuse side over the opposite side, giving me root 2 over 1, which just simply simplifies, to just root 2, okay? And then cotangent pi over 4 is just 1. Everyone good here? Okay, this is part of your Math Excel, so you will be doing this on your homework for tonight. And now we're going to transition into the actual identities. And identities can be kind of a tricky thing. Almost all these identities, unless I tell you otherwise, I will provide these when we take assessments. So don't feel like we need to memorize these. When you get into pre-calc, because that's what this is, like a big part of pre-calculus is the trig unit. So we're just kind of introducing it. We won't go quite as far in depth because you're going to get this all next year. This year I'll provide them, but next year when you're in pre-calc, you're going to probably have to memorize a lot of these different identities, right? So let's fill some of these things in, starting with the reciprocal identities. And what the reciprocal identities do is they take our trig functions and just take the reciprocal function of whatever its reciprocal function is. So we can say that sine of theta is equal to 1 over its reciprocal, which is cosecant. And that's one way to take reciprocals. So far, we've known reciprocals just to be the flipped versions, but the reason that they're flipped is if I take 1 over whatever cosecant is, that will always work out to be the reciprocal. Okay, so reciprocals are flipped fractions or 1 over our original value. Cosine of theta is 1 over secant of theta, and then tangent of theta is 1 over cotangent of theta. And then now just kind of doing the opposite here, taking the reciprocal function, so cosecant of theta, that's 1 over sine of theta. Secant of theta is 1 over cosine of theta. And cotangent of theta is 1 over tangent. So those ones aren't too bad. They just further reinforce the idea of the reciprocals. So nothing crazy there. Okay, now to the quotient identities. The quotient identities actually only involve tangent and cotangent, and they're just ways for us to express tangent and cotangent in terms of sine and cosine. So tangent of theta is also equal to sine of theta divided by cosine of theta. And I want to just kind of give a quick explanation for that. Because a lot of these, the reciprocals seem a little bit more obvious, right? That literally is the reciprocal. These quotient identities might be like, where the heck does that come from? So let's take this sine over theta divided by cosine of theta. And let's see about what do we know about sine and cosine? Well, in terms of the right triangle, sine is the opposite side over the hypotenuse. Okay, so that's just sine. Cosine is the adjacent side over the hypotenuse. And so now when I do this division, I have one fraction divided by another. So that's copy the top or leave the top the same and multiply by the reciprocal of the denominator. And so when we do this, the hypotenuse lengths divide out, leaving us with opposite over adjacent side, which is simply equal to tangent of theta. Okay, so that's kind of like a mini proof for why this quotient identity works out. Right, and the last one is cotangent of theta, which again, just the reciprocal of tangent, so ends up being cosine over sine. And we go through that same kind of mini proof there to show that by using side lengths of triangles. Okay, and then the last identities that we're going to work with today are called the Pythagorean identities. These are basically kind of derived from the Pythagorean theorem, hence the name Pythagorean identities. And so one of the most used Pythagorean identities is that sine squared of an angle plus cosine squared of that same angle is equal to 1. Now, just some notational things here. Notice where the squared is placed, and it's placed there for a specific reason. So when we see this sine squared of theta, know that that is really equal to the whole sine of theta, so whatever we'd want to evaluate sine of theta first, and then square it. Okay, so the reason that we put this squared after that sine is so that way we don't get it confused with this. Right? When I see this sine of theta squared without parentheses and with the squared being towards the end of that term, I'm wondering, is the theta being squared, so the angle, and then I take the sine of it? Or do I take sine of theta and then square the value? Okay, so that's why you don't typically see sine squared of theta written in this way. All right, so when we see sine squared of theta, remember we'll always find sine of theta first and then square that value. Everyone follow me there? Okay. Really important distinction. Okay, now two others that again can be derived using lengths of triangles and then also stemming from this. But the other identities are 1 plus tangent squared of theta, which equals secant squared of theta, and then 1 plus cotangent squared of theta, which equals cosecant squared of theta. And so when you're working on your homework, you're definitely going to want to have these out because they're going to get used quite a bit. Now, a lot of identity work, and we're getting to the point where, right, a lot of work with algebra, all the problems are kind of the same, right? We use skills that we already know. We can follow the same steps, use the same kind of concepts to get to the answer. But now when we're working with identities, there's not necessarily a clear-cut way to get to the final simplified answer. And you can be creative, okay? So a lot of these identities, you go, okay, what do I know about these values? And how could I rewrite them to eventually simplify? So there's a lot of trial and error. And know that you might have some ideas to start with. And as you work with those ideas, it might get you nowhere. And you might have to kind of start over, okay? So our goal with these identities is to find the value of the expression without using a calculator. And again, this is a really good way for us to practice. What do I know about cosecant? What do I know about tangent? What do I know about cosine? To try and simplify this term, right? So I'm looking at this and I'm thinking, you know what, cosecant, I want a lot of this to divide out. And right now I'm not seeing anything to divide out. So it just looks like a really long term that without a calculator, I'm not quite sure what to do. I do know that cosecant of an angle, I could use a reciprocal identity to write it in terms of sine. So I'm going to try that first. Let's write cosecant of 44 as 1 over sine of 44 degrees. And I'm like, okay, what about tangent? Well, right now, if I want to simplify this, I'm not seeing how sine of 44 dividing by sine of 44 is going to help me. So I'm like, okay, how about tangent of theta? I know that I can do two things. I see it in two places here, kind of excluding the Pythagorean identities because there's not anything being squared. But I'm seeing that I could write tangent as 1 over cotangent, or I could write it as sine over cosine. And looking at that quotient identity, if I write it as sine over cosine, well, I have sine of 44 in my denominator here, and then it'd be a sine of an angle in the numerator, and those would divide out. So I'm going to take this tangent of 44, I'm going to use the quotient identity, and say that tangent of 44 is equal to sine of 44 divided by cosine of 44. And that's going to allow these sines of 44s to divide out without me using a calculator at all. Right, if I'm multiplying by sine of 44 and dividing by sine of 44, they divide out. And now I have this cosine. And I'm like, wait, if I just leave that cosine as is, once again, we get the cosines to divide out. And what's left over? Just 1. Right, so you got to be willing to kind of try some different identities. There's not going to be a clear-cut way of, if you see one example, you just got to do more examples like this. You're going to have to be creative and willing to try some different things to come up with a simplified version here, right? I do want you all to try a couple. I have 1, 2, 3, 4 more. So let me do the next one, and I'll have you all try maybe C and D, and then we'll go from there. Okay, so now that I see this sine squared and cosine squared, this is where I'm thinking I probably want to use the Pythagorean identities. And I know that if I have sine squared of an angle plus cosine squared of an angle, so let me just write that so we can see this. So that identity being sine squared of an angle plus cosine squared of an angle equals 1. Well, I can rearrange these terms so that I get this sine squared plus cosine squared, which we could then just call 1. So in this case, all I'm going to do is rewrite this. So sine squared of pi over 3 plus cosine squared of pi over 3 and plus 2. So just rearranging the terms. And I'm recognizing this right here, the sine squared of pi over 3 and cosine squared of pi over 3 is just sine squared of theta plus cosine squared of theta, where theta is pi over 3. So that whole thing equals 1, and once I add 2, it ends up being just 3. There's actually more than one way to get there, so if you tried something different, regardless, you should end with 3, okay? But there are other ways. And let me just kind of mention some other things you can do with these identities. Like, let's say we didn't see to rearrange this. I could take this identity and we could actually manipulate it and solve for sine squared or cosine squared. So sometimes a common thing to do, I don't think you're going to need to do this with any of our identities that we're working on today, is I could take sine squared of theta and subtract cosine squared of theta, so I get 1 minus cosine squared of theta. This could have been used in this identity to replace sine squared of theta of pi over 3 with 1 minus cosine squared of pi over 3, which then would have canceled out with this cosine squared of pi over 3. So even our original identities, they can be manipulated or rearranged to then be used with all these kind of identity problems. And again, it takes practice. Okay, there's not one clear-cut way of finding all these values. All right, why don't you all try C? I'm seeing secant squared and tangent squared, so I'm most likely going to need to use some version of those Pythagorean identities. All right. Again, if I look at my Pythagorean identities, I'm noticing that I have one that's equal to secant squared of theta. That being 1 plus tangent squared of theta. So if I replace secant squared of theta, where theta is 23 degrees, with 1 plus tangent of squared of theta, those tangent squareds cancel out, right? I have a positive and a negative tangent squared of 23, canceling them out, leaving us with just 1. Not too bad there. Okay, but again, it takes some recognition. It takes some trying. And again, usually when we see that square, that should be kind of a clear indication to probably use those Pythagorean identities, right? Go ahead and try D. We'll just do this the rest of the way. Okay, I'll let you try it, see what you come up with. All I ask is that you try. It doesn't need to be right. Okay, but trying to work with these identities is just the easiest way to start to get the hang of it. So do your best with it. I'm going to go over it shortly. That basic Pythagorean identity, the basic one I'm referring to is the sine squared plus cosine squared equaling 1. And so again, it's all about the notation, okay? And that's why I made sure to make a note of that. So when I see sine squared of theta, well, I know that sine squared of theta equals 6/7. We're having to square that 6/7, giving me 36/49. And if I want to find cosine of theta, I'm going to first work to get cosine squared by itself. So I subtract this term over, get a common denominator, and then do the subtraction to get cosine squared of theta to equal root 13 over root 49. Okay, and that's what I wrote here. Root 13 cannot be reduced down. Root 49 is just 7. So cosine of theta is root 13 over 7. Totally, totally. Okay, and that's great. And those are connections that I want you all to make. So Evie is saying that she thought about sine of theta being the opposite of the hypotenuse. And then you could use kind of the Pythagorean theorem to find this other value, that root 13, and then take cosine to be the adjacent over hypotenuse. Okay, that's absolutely a way to come up with this value. I do want us practicing using that Pythagorean identity. So while you got that value and it works out, and that's perfectly okay, I do want to make sure that we still know how to kind of go about it this way. Okay, but that's great. That's thinking about other things we know about sine and cosine and triangles to find these values. Okay, so yeah, there's absolutely nothing wrong with that, but also make sure we know how to find values using this Pythagorean identity as well. All right, yeah, Dex. Um, don't want to square root. Think about like when we're solving. Let's just take like a x squared. Let's say minus 4 equals 20. Uh, Plus 4 equals 20. So if I were to go to square root both sides right now, and I'm trying to think about what times itself is x squared plus 4, I have no idea, right? When we think about what it means to take the square root, right? Square root means we're trying to find something times itself to give us what we're taking the root of. And so when we're taking square roots, we want to simplify that. And so like with this example, I would want to subtract 4, so x squared equals 16. And now when I take the square root of both sides, I'm not having to think about some weird kind of value or weird term that's what times itself is x squared plus 4. Does that kind of make sense? Okay, so that's why isolating the cosine squared is really important, because I know when I square root that, it's just cosine, right? But if I would have square rooted earlier at any point, I don't know what the square root of 36 over 49 plus cosine squared of theta is. It's not just that times itself is not what we're going to get here, okay? It all has to do with thinking about what it means to take square roots. Okay, great questions. One last example. We're doing just fine on time. The hardest of all of them, let's see how you do. Okay, see what you can come up with. I'm seeing lots of squared, so maybe some Pythagorean identities. Might need to use some reciprocal identities. I don't know. Let's see what you come up with. Again, all that I ask during these is that you just try and come up with something. This isn't the most obvious, okay? And again, this is kind of the work with identities. You try something, you see where it gets you, and then kind of go from there. My hint was that kind of breaking down the 4 divided by secant squared of 35, we can think of that as 4 times 1 over secant squared of 35. So I'm like, oh, okay, 1 over secant squared of 35 is equal to cosine squared of 35. Okay, as long as we're keeping them both squared, it's all the same. So then I can rearrange these terms like I did before. So I get 4 sine squared of 35 plus 4 cosine squared of 35. And I can't use that Pythagorean identity yet. But I recognize that both of those terms have a 4. So I can factor out the 4. So I get 4 times sine squared of 35 and cosine squared of 35. Getting this to be 1. 4 times 1 is 4 plus 2 is 6. This isn't an easy problem, not an easy identity, and it takes practice. Okay? That is it for our notes today.